Hello, this is Zhao Suojiang, a faculty member in civil engineering at San Francisco State University. Today, we're going to use an example to demonstrate what we learned before. Here is a simply supported beam. We have two concentrated moments. One is 10 kip feet, another is 20 kip feet. And the question was asking you to draw the shear and moment diagrams. And before you can do so, the first thing you need to do is to remove the support, replace it with the reaction force, meaning you're actually drawing a free body diagram for these structures. And with that, we're trying to figure out what are the reactions for AY, BY, and AX. Since we don't have any horizontal force, AX is equal to 0 from our past examples. To find AY and BY, one way you can do it is to sum the moment at point 8 using clockwise as positive directions. If you do so, what you're going to get is you're going to have this 10 kip feet external moment plus this 20 kip feet external moment. And you're going to have this By times the moment arm, which is 15 feet, since it's going to create a counterclockwise moment. Therefore, it is going to be negative. And with that, you're going to have your By is equal to 2 kip. Similar thing, you can sum the moment at point B using clockwise as positive directions. If you do that, you have the same external moment, 10 and 20. And you have the AY, which is also going to create a clockwise moment, is equal to 0. And your AY then is equal to negative 2 kips. The negative sign again means the directions of the force is in the opposite direction than your assumptions, since you're assuming AY to go up. If you calculate that AY is equal to negative 2, meaning your AY is in the direction going downward. And you can check using the force going upward, then the force going downward, to see if they are the same. If they're the same, meaning most likely the answer you're getting from above is correct. The force going upward, we're going to have our By is equal to 2 kips, and your AY is 2 kips going downward. They're the same, then we're okay. Another way to do it, as we mentioned in the previous video, is we have two concentrated moments, and if you add those up, it's going to be equal to 30 kip feet. And the force AY and BY need to create a force couple to resist that external moment. Therefore, your AY is need to be equal to your BY, and that's equal to the external moment divided by the distance between those two force couple, which is 15 feet, and that gives you 2 kips. Okay, same things. The theory behind this is if you have a concentrated moment, it doesn't matter where it applied to. It can apply to any place, and that is going to create the same reaction force at the beams. Okay, and with that, we can draw our shear diagrams. First, shear diagrams start from 0. It always starts from 0 and end at 0. If it doesn't, meaning you make a mistake somewhere. And you have your AY, which is going downward. That's equal to 2 kips, and that is going downward. And BY is equal to 2 kips. That's going upward. You start from 0 because the AY going downward 2 kips, you dropped the shear diagram for 2 kips. And because there's no external force between point A and point B, therefore the shear is going to remain constant, go all the way to point B, since we have 2 kips at point B going upward, that bring your shear diagram back to 0. All right. With that said, let's take a look how to draw our moment diagrams. I'm going to, since I know that the moment diagram going to have either a drop or a jump at the concentrated moment point, I'm going to have the dashed line draw down so that I know where the moment is going to change. The area for this one, this portion, let's say that's denoted as 1, 2, 3. The A1 is equal to A2 is equal to A3. That's equal to -2 kips times 5 feet. That's -10 kip feet. And we know that the moment at this point is going to be equal to the area of the shear diagram up to that point. The moment diagram starts from 0, and at the point right before the concentrated moments, the area for the shear diagram is equal to 10 kips, -10 kip feet. Therefore, the moment diagram is going to look like this. It's going to drop down to -10. We know this line going to be a straight line because the slope of your moment diagrams is equal to the value of your shear diagrams, and the shear diagrams is a constant. Therefore, the slope of your moment diagrams is also constant. Now, when we reach the point of the concentrated load, because we have a clockwise 10 kip feet moments, therefore our moment diagram going to have a jump, and that the value it jump is going to equal to the value of your concentrated moment. And you start from -10, you have a jump up with 10 kip feet, that bring your moment diagram back to 0. Okay, and from 0, the moment is going to equal to the area of your shear diagrams, and the area for A2 is equal to -10 again. Therefore, we're going to bring your moment diagram back to -10 again, right before x equal to 10 feet. And now at s equal to 10 feet, you have this concentrated moment, clockwise 20 kip feet. Then we'll bring your moment diagram off for 20 kips. You start from -10, now you have 20 kips feet, which your moment diagram will end up at 10 kip feet. And after that concentrated moment, the moment at this point is going to equal to the moment at this point plus the area of the A3. The area of A3 again is -10 kip feet. You start from +10 kip feet, subtract that, add that -10 kip feet, then bring your moment diagram back to 0. And here is how you can draw the shear and moment diagrams. I'll see you next time.